If you haven't seen one of these wave pendulums before, they're really neat. And in this video, I want to show you how to make one of these things in terms of how long to make each one of these strings for each of those balls to make it do a really cool thing. And I'll show you the video in just a little bit, but we'll save that for a little bit. So in our last video, we talked about simple harmonic motion and how the simple harmonic motion of this cart going back and forth can be described using the component of circular motion of something going in a circle. And we can find the position as a function of time, the velocity as a function of time, and the acceleration as a function of time. But at the end of the last video, I left off saying that this piece of it here is the same as that piece of it there. So if that is x, we can just plug in x right there. And we're going to do something a little further with this equation. But this gives us the acceleration as a function of its position. But the position is a function of the time and the frequency. So there's that equation. We're going to take Hooke's law, the force of a spring, and Newton's second law. Now, Hooke's law is often written with absolute values around this, but sometimes you'll see it with a negative out in front here and no absolute values. It just means that if the displacement of the spring is to the right, a positive value, we'll multiply that by a negative and get a force of the spring that's back off to the left, a negative value. Or if we displace off to the left, a negative value, a negative here and a negative here makes a positive force of the spring. What that just says is the force of the spring is going to always be in the opposite direction of its displacement. So we're just going to substitute this in for the net force. If we divide it by its mass, we can find the acceleration. So that's the acceleration of the cart as a function of its position, spring constant, and mass. Well, if that's acceleration, this is also acceleration. And we can clean that up a little bit. There's a negative on both sides, so we can cancel it out. And there's an x on both sides, so we can also cancel that out. And we're left with the spring constant divided by the mass is equal to 4 pi squared times the frequency squared. I'm going to go ahead and solve this equation for the frequency. I got to get this term away from the frequency, so I'm going to divide both sides by that. And then the frequency was squared, so I have to square root to get frequency by itself. And inside the square root here is a 2 squared and a pi squared. I can pull those terms out, and they were in the denominator, so they're still going to be in the denominator. So the frequency is 1 over 2 pi times the square root of the spring constant divided by the mass. Don't forget that frequency and period are reciprocals of each other. Period was how many seconds it took one cycle to happen, and frequency was how many cycles happened in 1 second. So if I just take 1 over that and 1 over that, I'll get the period. So I just got to flip it around. These terms are going to come to the numerator. That whole thing's going to flip around, and that is T sub S. What does S stand for? Spring. This is the period of a spring. The period of a spring equals 2 pi square root mass that's on the spring and the spring constant. So this equation is called the period of a spring equation. And if this mass is bobbing up and down, I could calculate, or I could measure its period, and knowing that in this case the period was 1.1 seconds, that's how much time it took to go from the bottom to the top, back to the bottom, the time to make a complete cycle. If I knew that, and I knew the mass on the end of it here, it was 200 grams, so 0.2 kilograms, well, we can calculate the spring constant. Just rearrange that for the spring constant, plug our numbers in, and our spring constant would have been about 6.5 newtons per meter. Okay, and that's kind of cool. Let's look at this example where and we talked about that in the previous video, but if this car is going down the road and it hits a big old pothole and that tire begins to oscillate back and forth at some frequency, well, we could find the period of its oscillation, the reciprocal of that. All I needed to know was the mass that is on that spring, the spring constant or the stiffness, and I could predict how fast it would take to go from the bottom to the top back to the bottom. In this example, I have the same mass on each of these springs, and those springs have the same spring constant. So it says that the period should be the same. But it's interesting that a variable that is not in here is the initial amplitude. So if I pull this one down really far and then that one not so far, they still have exactly the same period, the time it takes to make a complete oscillation. Amplitude was not a variable inside that equation that affected the period. Now in this example, I have the same mass on both of these, but the springs have different spring constants. This would have a much smaller spring constant because that amount of force had to stretch the spring a lot farther to produce a force equal to the weight. This would have a larger spring constant. So looking at this equation, which of these two would have a larger period? Which one would take more time to make an oscillation? Well, they had the same mass, but the one with the smaller spring constant is in the denominator. The one with the smaller spring constant would have a bigger period. This was the smaller spring constant, and so we pull them down like this. It's going to take longer for this one to go back and forth. And indeed it does. Now the spring constant is inside the square root here. So if the spring constant were 4 times as big, let's say this spring constant was 4 times as big as this one, what would it do to the period? Well, it's going to be inversely proportional to the square root of something 4 times as big. So it would only be half as long. Okay. In this example, they have the same spring constant. So this is the same type of spring, but they have a different amount of mass. This was about 100 grams and this was 200 grams. So the 200 grams stretched the same type of spring further, and I just have them started at different heights to make them start out in line. But same spring constant, more mass. What's that going to do to the period? Which one is going to have a larger period? Well, more mass in the numerator is also going to be a longer spring constant, and so this one should take longer to go back and forth. And you can see that this spring here had a longer period. It took more time to go back and forth. Now, if I wanted to have a period of a spring to be 3 times as much as the period of another spring, like if I wanted the period of this to be 3 seconds when the period of this one was only 1 second, what would I have to do to the mass to make this 3 times as much? Well, I would have to have 9 times as much mass on there. 9 times as much mass here when we square root would change that by a factor of 3. So that's a little bit about period of a spring. Now let's look about the period of a pendulum. So we have T sub P, that's the period of a pendulum. And this time, it's the variables that give us the period of a pendulum is the length of the pendulum and the acceleration of gravity. And it was actually Galileo who worked all this out when he was just still a student. But he was sitting in this cathedral, and this cathedral is in the town of Pisa. You might recognize the bell tower of Pisa, often called the Leaning Tower. But in that cathedral was a chandelier. And it wasn't actually this chandelier. It was that chandelier had been replaced. This was the original chandelier that was there when Galileo was observing it. And that now hangs in a little museum, maybe just 200 yards or so from the original place. But what he would do is the doors would be open and the wind would blow, and this thing just might sway back and forth ever so slightly. Or sometimes the wind would blow a little bit more, and instead of just swaying back and forth ever so slightly, it might swing maybe not quite as wildly as I've shown there, but it would swing more. And Galileo observed this and timed the period of the pendulum using the most accurate clock he could think of, which was his resting pulse. So he would put his fingers on his wrist and count how many heartbeats it took for this thing to go back and forth. And he found that the period of that pendulum did not matter on the initial amplitude. So if it was just swinging back and forth a little bit or swinging back and forth a lot more, the period didn't matter. And he was later able to work out that it was just the length and the acceleration of gravity that did that. So the period of a pendulum. How long does it take a pendulum to make one swing back and forth? Well, just like we did with a mass going back and forth between two springs, we compared it to circular motion and found components of that. And we're going to do the same thing here. Or you might just be satisfied with me saying that it's going to be a very similar process, and this is the equation we come up with. I think I'll leave it at that. It's going to be the same and same process. So let's look at some variables that change it. So the length of this pendulum is, of course, longer than this one, and when we pull them back and forth, a longer length should make a longer period. And you can see that this one does take longer to go back and forth. Well, what other variables affect it? Here these two have the same length, but they have different masses. And what's that going to do to the period of a pendulum? In fact, this one has maybe 5 times as much mass on it. What's that going to do to it? Well, when they swing back and forth, they have the same period, because we can see that mass is not a variable that affects the period. The only thing that affects the period is the length of the pendulum and the acceleration of gravity. So if we were to take this apparatus to the moon, where there was a smaller acceleration of gravity, it would take a longer period. All right, so here's this wave pendulum that I was talking about at the very beginning. So each of the lengths of these strings are very carefully measured, so it does a really neat thing. So they all start out in unison, and you can see that these go back and forth fairly slowly. They have a long period. These go back and forth much more quickly. They have a short period. But every one of those pendulums has a different period. And it looks all chaotic, and it's like, oh, what a mess. But right there, half of the time has gone by before they all come back together again. And when I made this so that all these pendulums would all swing back finally together after exactly 45 seconds. So 45 seconds right there, they all come back in unison. And when I made this one went back and forth 25 times in 45 seconds. And this one went back and forth exactly 26 times in 45 seconds. And the next one is 27 times in 45 seconds. Each pendulum here made one more oscillation or cycle in that 25-second period, and after 45-second period, so after 45 seconds, they all finish that last oscillation. So let's get into a spreadsheet here, and if you wanted to build one of these things, the spreadsheet will show you how to do that. So this is the spreadsheet that's going to allow you to calculate how long to make each one of these pendulums. Now there is a link in the description of this YouTube video to this actual spreadsheet, so you can go through the calculations yourself. The first thing we need to decide is on some of the design parameters. How tall do we want this device to be? Do we want it just to sit on a shelf somewhere, or do we want to really go big and make them out of like bowling balls or wrecking balls or something really, really big, and where the strings here are 30, 40 feet long? Okay. On the one I built, the initial length of the longest pendulum was about 1 meter. And that was just a nice size. And you certainly don't have to build it as nice with wood and stuff like that. It can be junky and you can still impress your friends. Now we want to decide how much time elapses before the overall pattern repeats. In the video I just showed you, they all came back together after 45 seconds. And you might want to reduce that down to like 30 seconds. If you do that though, the patterns, it moves through the patterns kind of quickly and may not be as recognizable. If you chose it to repeat after a much longer time, like 5 minutes, people might lose interest. So you decide how much time before the overall pattern repeats. And maybe 60 seconds would be a good one for this one. So after 60 seconds, all of those balls are going to come right back together. So based on those design parameters, what's going to be the period of our longest pendulum? So I decided how big I wanted to build it. Now we can use that length and gravity to figure out its period. So we are going to say as a function 2 times pi, and we can get the number pi by putting an equal sign, pi, open close parentheses, and that would give us lots and lots of decimals of pi. I'm going to click there. So I have 2 times pi times the square root of L over G. SQRT is our function for square root. And I need to take this length and divide it by the acceleration of gravity. Now that's the acceleration of gravity where I live. It's actually 9.79604 meters per second squared. You could look it up and figure out what it is for your location. Okay, but it looks like a 1 meter long pendulum is going to have a period of a little more than 2 seconds. Okay, so now we want to find the number of cycles the longest pendulum makes in the time for the overall pattern to repeat. So if it goes back and forth once every 2 seconds, how many times is it going to go back and forth in 60 seconds? So that's just going to be this number divided by that. Okay, and it looks like it's going to go back and forth a little less than 30 times. Now for this pendulum to work, we need to have it just come back exactly 30 times. So now we need to round the number of cycles for the longest pendulum to the nearest whole number, which is 30. And the cells do turn green when I do incorrect formulas. So that's going to be, this pendulum here is going to go back and forth 30 times in 60 seconds. This one's going to go back and forth 31 times in 60 seconds, 32 times in 60 seconds, and so on. So we now want to calculate this whole table here. The number of whole number of cycles for my first pendulum, my longest one, is just going to be equal to that number. I don't want to type in a 30 because I want to be able to play with this and say, okay, maybe I need to change the height, maybe I want to change this or that. But by referring to these cells, we only have to change it in one place and it changes in every place. So the number of whole cycles for that longest pendulum is going to be 30. This one is going to be that number plus 1. And then I'm just going to take that formula and copy it down for each of my 15 pendulums. Okay. Now, we said this was an initial period of the longest pendulum. It was going to take a little more than 2 seconds if it was 1 meter long. But we want to make it not 29.88792 so on cycles in 60 seconds. We wanted to make it exactly 30 cycles. So we have to change the period slightly, and we're going to do that by changing the length slightly. So the period of each of our pendulums, we have 60 seconds to go back and forth 30 times. So what's the period going to be? It's going to be 60. And I do want dollar signs around that so it always refers to that number as I copy my formula down. We're going to take the 60 and we're going to divide it by this number here. Okay, and I don't want dollar signs here because when I copy it down I want it to use that number. So and we know the answer, it's going to be 2 seconds because if it goes back and forth exactly 30 times in 60 seconds, the period must be 2 seconds. So now we're going to copy that formula down, and the 15th pendulum down here was going to go back and forth 44 times in 60 seconds. So its period must have been 1.364 seconds. All right. Now, we know what period we want the balls to have. We need to decide now how long to make each pendulum. So we need to rearrange this equation for the length of the pendulum, because that's how we got to decide how long to make each of those things. And so we got to rearrange that. If you need some help, you could select that and delete. And if you didn't need that help, then don't delete it. Practice those skills yourself. But now the length of it is going to equal the period squared. So this period raised to the power of 2. No dollar signs on that because each period is going to be different. But then I do want to multiply it by gravity. So the period squared times gravity, and I do want dollar signs on gravity because it's always going to refer to there. Now I'm going to divide by 4. I'm going to divide by pi with dollar signs raised to the power of 2. Okay, and maybe I should say that dividing by 4 and dividing by pi squared would be the same thing as dividing by parentheses 4 times pi squared. It just saves keystrokes. Okay, so we decided that we wanted to build about 1 meter tall, but we now know that it needs to be 0.993 meters tall to get us exactly the right number of oscillations. So now that formula we're going to copy down, and that's how long each of those pendulums need to be to do that really cool thing. I want to encourage you to just, even if it's not beautiful, try it and see how close you can come, because it really is neat.